Hello ladies and gentlemen, welcome back to what is the 8th laboratory for GGS300, Quantitative Methods for Spatial Science, and this is the laboratory which basically accompanies the 10th lecture which has been carried out this semester, so that was focusing on the analysis of variance and the Crisco-Wallace test. So in this particular session today, what we're going to be doing is we're going to actually just be providing a small amount of code which basically just captures those two different tests that we covered already within the lecture. So this is going to be relatively simple and thankfully very short. So for you, you're going to have a week where you're not going to have too much work to do, which is nice. And as a consequence, this video isn't going to last very long. We're going to get through this material pretty quickly in probably about 20 minutes or so. What I will say is that this particular example that we're going through is actually taken from the book, so you can go and take a look on there, page 180, 181. It focuses on the 3 different house price samples that we'll be using, so 4 different house price samples that we're using here for those, as an example, for those cases where you have 3 or more samples that you want to test as to whether they've come from different populations or whether they may be from the same population, okay? So without much further ado, let's get started. So essentially we have these 4 different samples here. So let's assume that these are from 4 different places. I've sent you out 4 different neighborhoods to collect data on house prices. And this is essentially what we end up with. So we're able to put these 4 different samples into the global environment just by executing the block of code that I've selected with blue. So you can obviously just press run. I just like to press Control Enter, and that enables me to run through the code quicker. We then can allocate the price column to that. So basically what we're doing is we're taking all of these and creating an array called price. We can then create one as well called group, which basically just allocates the group number to these. And then when we actually just put them together like this, all we're doing is we're taking those individual samples, which are arrays, combining them together and then putting them into a data frame. Okay, so this should be kind of fairly straightforward to you now. Every week we kind of take a small amount of data and just kind of manually create a data structure from it for us to analyze. And that's kind of in contrast to when we load stuff in, maybe as a CSV or a .text file, which you've done in the homeworks, for example. And generally that's how you're going to be loading your data. It's just that in this particular example, it's also good to know how to do things manually, particularly if you've got to produce a reproducible example because you're stuck on a problem and you're posting it on a forum, for example, like Stack Exchange or Stack Overflow. People want to have a reproducible example that kind of mimics the issue you're facing so that they can look at the code you've got, produce the data, and then give you an answer back, which obviously helps if you're stuck on something. So that gives us the data frame up here for this particular case. We can create a box plot out of this. So we're very familiar with box plots now. So we've got the price over here on the y-axis, and we've got these 4 different categories. So obviously a box plot is where you use individual categories on one of the axes, and you're showing the distribution. Okay, so remember we've got the range here and the interquartile range and then the median. Okay, and this is for those 4 different neighborhoods. In this particular example, I just gave it each one of the data structures. We could create exactly the same plot just by giving it the array for each price and group. Okay, and you can see the tilde here is used to indicate that you want these on different axes and that these are basically able to be plotted. And we just get exactly the same output, but without the nice labels, which obviously, if you're handing in a piece of work or if you're writing a research paper, then you need to have your graphs fully labeled with a title, make sure that they're, conforming to those gold standard scientific processes that you need to meet in order to excel on this course, but also to meet scientific protocol when you go out either to work in a workplace or to work in government or to start a business, whatever you're going to do, okay? So we can also create box plots, and we can use the notch argument here where I've placed it to true. Basically, this gives us an indication as to the distribution of the data points, and it tells us about, so the width of the notches gives you an indication as to how the data are structured under there. There are many different ways that we could show this. We could just like I prefer in ggplot2, we could just plot the actual underlying data on top of the box plot, and that would give you an indication as to where the clusters are. There's also violin plots, which are kind of similar to this, but just give you an understanding of where the distribution is. So there's lots of different ways for us to visualize those distributions. This is just one particular way. Obviously, we haven't labeled anything here, so that's an issue, but normally you'd want your full axis labels and label these categories as well, place a title. Great, so that just gives you a bit of an introduction to the data which we brought in. Now what I want to do is for us to actually move on with the Anova. So this is for our normally distributed data. So let me just go back to what we covered in the lecture. Great, and we have these 6 different steps, okay? You remember that that's essentially, sorry, not 6 different, 3 different steps with 6 required calculations. So we have the calculation for the between group variability, and then we have the calculation for the within group variability, and then finally we calculate the test statistic, in this case the F statistic, okay? And we have all of these requirements that need to be met. So we need to have 3 or more random samples. Great, we've got that. Independent data, normally distributed data, great. Populations with equal variance, and then continuous data. Okay, so we basically meet all of those in this case with the data that we've got. But now what we need to do is actually load in some of those, we need to create some of those data parameters that we need in order to start with the calculations. Okay, so we know that the final step to get our F statistic is just to take the MSB, so the between group variability, and divide it by the denominator here, MSW, which is the within group variability. So that's a very simple division. But what we need to get first is these actual other interim calculations, and they look really scary, but they're quite simple in reality. So we need to make sure that we get these other metrics just here, okay? So what we're going to do is we're going to get the length for this sample. I'm going to label it N1, so the length of sample 1. We're going to get the mean, so it's going to be X bar 1. And then we're going to get the standard deviation, so it's going to be S1. Okay, so the standard deviation, this is all for sample 1. And then we can basically just load all of those in for each one of the samples, so all the way up to sample 4. And that just provides us with some of these key input factors, okay? So we've got the mean, the number of observations, we will get the number of groups overall, and we'll also from this be able to get the total number of observations. So here we are on step 1, so that's what we're going to do here. We're going to find the X bar T. And essentially first what we need to do is we need to so we're going to create an array of all of the number of samples, so all n. Let me just find that for you. Here we go, we've got an array here which contains those 4 different digits, and those digits are the sample sizes for each of those 4 samples. We then need to get all of the sample means, so we place that all x into the global environment here. And then finally we can just sum all of the all n category in order to get the total number of observations in the sample, okay? So that's this, this capital N term here. And then finally what we can do is we can get the X bar T. So what we're doing is we're going to sum the multiplication of all of the individual sample sizes by the actual relative mean, and then divided by the number of total observations across all of the groups. Okay, so that's essentially what we've got here, the X bar T. We're going to multiply the n for each sample by the mean of the sample, and then eventually we're going to sum them all as the numerator, and then we're going to divide it by the denominator here, which is the total number of observations in all the samples. Great, so now let's get on to part 2 of step 1. And that's here, we need to get this SSB value, okay? So before we were focusing on the total weighted means of all the samples. This time we want the between group sum of the squares, okay? So you're very familiar with the sum of the squares because we've been through this before. But this time we just have this additional component that we need to get, okay? So for all of the sample means, we're going to subtract that X bar T value from each one of them. And then we're going to square them, and then we're going to multiply them by, in this case, this ni, so this number of observations in the sample. relative to each one, and then finally we sum it. So we just basically end up with this SSB value here, which is 6,769. Okay. So we've got the X bar T, we've got the SSB, and then finally all we need to do is just to get this one MSB a metric down here, and it's very simple. So these look more scary because they're big and long, but the reality is once we're down here, we just take the numerator from here, the SSB, and then for the denominator, we just need the number of degrees of freedom. Okay, so that's fairly simple because we just need the number of groups minus 1. Okay, so what we're going to do is we're going to first get the K. So the K is the number of groups that we have overall. So we can just take, for all of the samples, we can get the length of them, and that should be 4. Okay, so that's right. So when we enter that into global environment, we get 4, which is sensible. And then we just need to do the actual calculation. So it's going to be the SSB divided by K minus 1, which is obviously 3. So when we do that, we get the MSB value up here, which is 2,256. Okay, and that is the between group mean squares. So that should be fairly straightforward. Now what we need to do is to get this within group variability here. So you'll remember in the previous lecture, what I was doing was we're focusing on where the means actually are relative to each other. Okay, so when we talk about the between group variability, that's what we're talking about, the distance between those different means for each of the samples. Whereas the within group variability, what we're talking about here is just the distribution of the values for a single sample. Okay. Great, so what we need to do here for the within group sum of squares is we need to get this SSW term. So we need to subtract 1 from the total number of samples in that sample multiplied by, and this is the standard deviation squared, so it's the variance of the sample. And then we need to sum that for all groups, all the Ks. Okay, so the number of sample groups that we have. So first we need to put all of the standard deviations into this array, all S. And then essentially what we need to do is we need to sum the components of this this particular equation here, and that provides us with the SSW value that we're looking for. Okay, so we get that down here as 6193. And then once we've got that, it's fairly straightforward for us to get this final part. So we just need to take the SSW value as the numerator, and then for the denominator we just need the number of degrees of freedom, which here is the total number of samples, n, capital N, minus the number of groups that we have. So let's see if we can do that now. So we've got the total number of samples here is 22, and we've got the number of groups 4, so it should be 18 that we end up with as the denominator, which it is there. And now when we input all of this into the memory, MSW, what we end up is with this 344 value. So that should be fairly straightforward. We've done this this first step here to get the between group variability, and then we've done the second step here to get the within group variability, and then all we have to do very, very simply for that final step is just to basically divide one by the other and get that F statistic here. Okay, so that should be fairly straightforward. So we can take the MSB and the MSW, and we can get the F statistic here, which is quite high, 6.55. So actually we can then use the F distribution function to get a p-value for that size test statistic. So this F distribution function here, I mean, it's exactly the same as all the other ones which you've used now. So you've used the Z distribution, you've used the T distribution, and now you're using the F distribution, and it works in exactly the same way. So you can get, you can provide it with a quantile, you can provide it with a probability, you can get a density. You just need to know basically what you're providing it with, so you need to give it, in our case here, what we're doing is we're providing it with the F statistic. And then basically we're giving it the number of degrees of freedom, and then it provides us with an indication as to the p-value, which here is really quite highly significant. So you remember that our significance value normally is 0.05, so that's where we can be 95% confident that the results haven't just occurred by chance. That gives us only a 5% error margin, which is quite reasonable. So that's what we're looking for here, and this p-value is obviously really quite far below that 0.05 level, okay? So that's quite nice. We calculated that by hand. Let's now look at how we do that manually, sorry, automatically, because obviously if you know these tests, then you're not going to sit down, you're not going to tap all of these lines out when you can just basically run this test in a one-liner and get a sensible result from R. So what we're going to do now is we're just going to generate that test automatically using the inbuilt functions. You can just look at the one-way test here, which is the way that we do Anova within R. So you can take a look at the description and the different arguments for this particular approach. Essentially, if we provide the one-way test with the price and the group data, then we get a set of results, and that gives us a one-way analysis and mean. So we get the F statistic here, 6.558, which is the same as our manual test statistic. And we get a p-value of 0.03, which is the same as our manually created p-value of 0.03. So that's really nice. We have the manual way that we created the test statistic, and then we have the automated way. So basically the way that you will use this when you go off out into the world after you finish this class, and you don't have to show Ed anymore how you do this manually. You can just use the automated way, and hopefully you'll have that kind of solid statistical understanding so that you can use these tests without needing to do the kind of laborious manual calculation that we need to do here, just so you guys actually understand the process of obtaining those test statistics. Okay, great. You are able to produce Anova tables, as I've just demonstrated here. It produces the same results, essentially, for just using different functions. So I think that's fairly straightforward. I talked about the relevance of these asterisks when we were in the lecture. So hopefully that's reasonably clear here. We're getting a reasonably strong result from this p-value that we obtained. So that's quite interesting. Okay, now let's just finish off quickly with the Crisco-Wallace test. So this is obviously if you have data and it doesn't conform to those parametric, normally distributed assumptions that we need the data to conform to in order to do those types of tests, such as Anova, then basically you might have to downgrade that data into ranks and actually run this non-parametric test, so for non-normally distributed data, okay? So when our data don't conform to that lovely bell-shaped curve, maybe it's quite heavily skewed one way or another, and as a consequence we have to fall back on these approaches that maybe don't consider the arithmetic mean, they consider the mean across the different ranks that we have across our samples, okay? So I want to clear the global environment, but we're going to need some of these. So let me just try and run this through now. The code that we have here is very simple, very short, and hopefully you'll then have a good understanding as to how we generate the data for this test. So we have the data frame here. So these are all of the prices for the properties that were surveyed for all of those different groups. We can allocate ranks to them now. So just from the smallest value going down to the highest value, we just literally say, okay, this is the smallest one, it gets row 1, rank 1. This is the second smallest, this gets row 2, so the rank 2, and so on and so forth until we get all the way down to the bottom of the data set. And we've got 22 values in this data set, so obviously the final row is going to be rank number 22, okay? Great, and what we then want to do is want to get the sum of the ranks for each sample. So what we're doing here, and this looks long, but I remember telling you in the previous cases, if you get a piece of code like this and you're not sure what it does, just break it down into little bits. You know, it always reminds me when you're starting to read, I remember as a child my dad saying, if the word's really long, then break it down into those components that you can easily pronounce. And then once you've got those points, you just basically put them all together and understand how the words said as one full statement. And it's kind of the same with code, right? So here was basically saying go to the data frame, frame 1. So frame 1 is just here. We then want to use the $sign, so we're talking about we want to access one of the columns in there. And what we're basically saying is we want to get the ranks data. So if I just print this to the command line, these are all of the ranks that we have within that data frame. And we want to basically sum them. So it's saying sum all of the ranks in the data frame. But what we do here when we actually use these square brackets is we're saying, give me the ranks in this data frame, but only for the groups which equal 1, okay? So this double equal is what you do when you're saying that something is a matching condition, as opposed to just a single equal where you're kind of assigning that value to that particular row, for example. So when we actually just run this individual segment without summing it, what this is doing down here is it's returning the ranks for all of those rows that are in group 1, okay? And then when we actually sum them together, what we end up with is 52, which will be the summation of these 6 ranks just here, okay, for R1, so the ranking sum for the first sample, okay? Well, I hope that that's finally clear to you now, and we can move on to the next part. So I'm just going to add those ranked sums into the global environment for R. So you can see R1, R2, R3, R4 for each one of these. Next, what we can do is we can put all of those rank sums that we've got into a single vector, a single array called all R. So we can put that up here, and that has all of our rank sums up here for all the different samples. And we can also do the same for all of the sample sizes. So we actually specified these N1, N2, N3, N4 further up in the script, but it's just saying, give me an array where all of the relative sample sizes are being stored. And finally then, what we can do is we can get the sum for all n, and that provides us with the total number of data points that we have overall, okay? And we can just put that into our global memory. So when we do that, we get the 22 value that we had before. So we'll remember that in the Crisco-Wallace test, we need to get this quite cumbersome equation over here. So we want the H test statistic, that's what we're trying to calculate. But to do that, we need to have the number of total observations in all samples. We need to have the number of observations in just this sample. We need the sum of the ranks, which we've already got. So basically got all of this existing information. Depending on whether we've got tied ranks, so some rows which equal the same ranking, then you need the G here and the TI, okay? But I think we in this particular example, I don't think we need them explicitly. So what we need to do is to get this equation just here, which means that we need to get the H statistic. So basically we need 12 as the numerator. For the denominator, we need the total number of samples multiplied by the total number of samples plus 1, okay? Multiplied by the sum of this here, so this bracket, so all of the the sum of the ranks squared divided by all of the sample sizes minus 3 multiplied by the total number of samples plus 1. Okay, so it's a bit of a long one, but it's hopefully not too complicated for you to see, and that produces our test statistic of 10.46 here. And then what we can do is we can just go to another function that we have. So if we go here to p chi-squared, this is just another inbuilt R function which allows us to access that chi-squared distribution. So here it's the H distribution basically, so that's what we're using. So you can again access the density, the probability, the quantile, or you can just generate a random number from the chi-squared distribution. And you can use this in just the standard way that we've used all of the previous functions for looking up probabilities. So we're just going to go p chi-squared. Here we're going to give it the H statistic, and then we're going to give it the number of degrees of freedom. So that's just all of the samples that we have, so the length of them minus 1. And that should give us a p-value that we can then use. So 0.01, so that's a significant p-value. It's below that 0.05 that we're looking for to be 95% certain that our results haven't just occurred by chance. That means that the error is just 5%, which is an acceptable level of error in this particular case. Okay, so that gives us quite a nice result. And then obviously we want to just check that using an inbuilt function. So we have this Crisco.test in order to be able to test this data in an automated way. And when we do that, we end up with a chi-squared value, which is basically the same. So it's 10.4. So it's the same as the manually created one here with a little bit of rounding error. And then we also get the same p-value, okay, so 0.01 we get down here for the p-value. So that means that now for both of these tests, we've been through the kind of manual way that we've calculated it, and also you've had the opportunity to see when you've spread your wings and you've gone off into the world, you don't have to follow what I set you, how to do these automatically. So nice and easy. And actually a trained statistician will basically be able to rattle through a whole load of tests really quite quickly as they go through that kind of exploratory data phase. So they'll be able to graph some distributions for data, they'll be able to build models very quickly on the fly. And that's a really great skill set for you to be able to have, and it's going to become more and more important as we get into the future, and computers are going to be the fundamental backbone for how we make decisions in a whole load of those technical scientific areas where very often the best jobs are. Okay, great. Well, I won't keep you, and it's very nice to see you all, and I hope you have a good week, and reach out to me if you've got any further questions. Thank you. Goodbye.